Mm-hmm.
Oh my gosh, I don't understand this incline plane, bro. I'm gonna fail this quiz, bro. I need some help. Steven!
You rang.
Bro, I don't even get this incline plane stuff. Like, how does this even work?
I do not understand it. It's so easy.
Well, first of all, like, how do you even get the force of it?
Force is mass times acceleration. An object accelerating at 10 meters per second squared with 5 kilograms of mass will have 50 newtons of force. Now do you understand it?
So, like, if it's like the normal force, how does that work on like the triangle thingy?
Oh, you see, when a box is not on a flat surface, you can split its force into different components. This force F here is going at approximately a 45-degree angle. We can split it into its vertical and its horizontal components using trigonometry.
Damn.
Like in this scenario, we have a 3 kilogram box on an incline of an angle theta. The 3 kilogram box has a force of gravity acting on it like this, but not the entire force of gravity is going to pull it down the ramp. It's only going to be a certain component of the force.
That's crazy.
But how exactly do we do that?
Oh, it's done. Perfect. So basically how that works is when there's a force right here, we gotta split it up into portions. So if you want to look at the vertical force, what you're gonna do is you're gonna look at the force of y, that's the vertical component, that's the force times the sine of the angle, times the sine of theta, which is this theta angle. Let's say you want to find the horizontal force going that way. You're gonna do F cosine that angle, just like in regular triangles, you know?
Hey, now that I helped you, can you help me? I don't really understand normal force.
Normal force, bro, that's like the easiest thing. Okay. So look at this. We got a box. Gravity's coming this way. Normal force is the thing that holds it up. So that keeps it at velocity of 0, and it also means that the normal force is equal to the force of gravity.
And because the forces are equal, they don't go anywhere?
Yeah, like this box right here. Gravity's pulling on it, but the normal force of the table is pushing it back up. That's why it's stable.
Okay, thanks for helping me.
Anytime, bro.
You know, he never did tell me, what if there is no force pushing on an object? What if it's just gravity? I have to find him. Show he is.
What are you doing?
What are you watching? Oh, you, K-pop. Hey, Robbie, I need some help. You never answered my question. What if there is no force?
What?
What if there's no force on the object? What if it's just gravity?
Oh yeah, of course. Basically how that works is it's Fy, and if there's no force, you just do mass times gravity, because that's the only force acting on it. Duh. Mass times gravity sine theta, mass times gravity cosine theta.
Thank you. And now it's time for some multiple choice questions. Block A is placed on a rough surface inclined at an angle theta above the horizontal. A taut string connects block A over a pulley to block B, which hangs from the string as shown below. The masses of blocks A and B are m sub A and m sub B respectively. At time t equals 0, block A is sliding up the slope as block B falls, and the blocks are both slowing down. Assuming that the mass and friction of the pulley are negligible, if the mass of block B is 2 kilograms, the gravitational force exerted on block B is most nearly which of the following? So let's revisit the question. It tells us that this diagram is what we need to look at. And it tells us that m sub B is falling down as m sub A slides up the ramp. Now for this problem, we can ignore that it's on an inclined plane, because the only thing the question is asking is what is the gravitational force on block B? And to calculate gravitational force, we take the mass of the object and we multiply it by the gravitational acceleration. Now on Earth, the gravitational acceleration is about 9.8 or about 10 at 2 kilograms. We multiply it times 9.8 and we get 19.6. Now this 19.6, it's not exactly 20 newtons, but it says most nearly which of the following. So we're going to circle 20 newtons, and that is our final answer. We also know this is true because we can eliminate the other answers. We also know this is true because we can eliminate the other answers. For choice A, the only way that the force would be less than the mass is if the acceleration was less than 1. And since the acceleration on Earth is 9.8, it is obviously not less than 1. We can eliminate choice A. Additionally, we can eliminate choice B because we know that the acceleration is not 1. If the acceleration on Earth was 1, then we would multiply 2 times 1, giving us 2. But since it's not 1, we can also eliminate B. Now, we can eliminate D because we do not need the mass of block A to determine the gravitational force acting on B. If the question were asking for the total force on the system, we would need to know the mass of block A because we would use the mass of block A, and we would also need to know this angle of theta in order to determine the normal force and the force of friction. So we would need to know the coefficient of friction in order to combine all those factors and calculate the net force. But since this question is not asking that, we can eliminate choice D. This next multiple choice question tells us that a 5-kilogram object is released from rest near the surface of a planet such that its gravitational field is considered to be constant. The mass of the planet is unknown. After 2 seconds, the object has fallen 30 meters. Air resistance is considered to be negligible. What is the gravitational force exerted on the 5-kilogram object near the planet's surface? So first, let's draw this out. Here's the planet, here's the object. We know that it's 5 kilograms, and we know it falls 30 meters. We also know that the acceleration is constant because it states in the question that the gravitational field is considered to be constant. We also do not know the gravitational acceleration. We only know that it is constant. We need to find the acceleration in order to find the gravitational force. In order to find the acceleration, we take the distance the object has fallen and we set it equal to 1/2 times the acceleration times the time it took to fall plus the initial velocity times time. Now, we know that since the initial velocity is 0, because the question states that it is released from rest, we know that the initial velocity is 0. And 0 times any number t would be 0. So it's the same thing as adding 0, which means we can eliminate this entire part of the equation, and we get s equals 1/2 at squared. Now, we isolate t by multiplying both sides by 2. We get 2s equals at squared. And dividing both sides by t squared, we get a equals 2s over t squared. Now, we plug the numbers into our equation. So we get a equals 2 times the distance it fell, which was 30 meters, divided by the time it took squared. We know it took 2 seconds, so 2 squared. Putting this into our calculator, we find that it accelerated at 15 meters per second squared. But this number 15 is not our answer because this is only the acceleration, not the force. However, we know that the only force acting on this object, or we assume that the only force acting on this object is the gravitational force. And since the only force acting on an object is the net force, and we know that the net force is equal to mass times acceleration, we can say that the force of gravity is equal to mass times acceleration. Now, we know our mass in the question is 5 kilograms. So we take 5 and multiply it by our acceleration of 15 meters per second squared, and we get 75. So we know that this object had a force of 75 newtons acting on it as it fell.
Yeah. Okay. So in this FRQ, we have an inclined plane right here, and this is the angle formed in its sine, and the angle is theta. Then we have a block right here of mass m, and it's being pushed with a force of F. In this FRQ, we have to label all the forces acting on this block. We also have to develop an expression using mass, theta, the coefficient of friction, force, and gravity for the block's acceleration up the incline. But we also have to develop an expression for magnitude of the force that allows the block to slide up the plane with a constant velocity. So how we do this is, on this we have force F pushing on the block this way. And then we also have our coefficient of friction. Our force of friction pushing down, because if the block is sliding up, there has to be friction pushing it down. We also have mass times gravity acting straight down, as usual on all things. But then we also have the normal force going this way, because the inclined plane is pushing this way. So the normal force is going that way. That's how we do the diagram. In the second part of the problem, where we have to develop the expression for the block's acceleration, what we're going to do is find the net force, and the net force is mass times acceleration, which is also equal to the force of the block pushing up minus the force of the block pushing down, because it's going up, so you have to find the net force of that, which is F times cosine theta minus the force of friction minus the force of x. You see right here, this is the force of x, which is equal to the force of friction. So that's where we get that from. This is the thing that describes everything that we're doing here. Then we have mass times acceleration equals, we bring this down, force times cosine theta, and then instead of force of friction, we use the coefficient of friction times the normal force, which is the formula, minus F sine theta. That's where we get this from, because if F is going up, there's no mg, it's just the force pushing up on it. So it's F sine theta, because we're looking for the vertical component of that. Then we bring this down again, so we have mass times acceleration, so we'll just bring that down for all of them. Force times cosine theta equals coefficient of friction times the force of y. In this one, we're also going to use y in this. We're going to have x this way and y this way. Y is equal to the normal force and also equal to mg cosine theta. So y is right here, and then we also have mg sine theta, which is equal to the f sine theta, because f is equal to mg. Bring this down again, we'll have f cosine theta equals coefficient of friction times mass times gravity cosine theta plus f sine theta, because that's where this comes from. And then we'll just bring this down again, so mg sine theta minus that. F cosine theta equals the coefficient of friction times the mass, because we're going to multiply this using the distributive property. Coefficient of friction times mass, gravity, cosine theta minus coefficient of friction, F sine theta minus mg sine theta. F cosine theta minus coefficient of friction times F sine theta equals, minus the coefficient of friction times mg cosine theta minus mg sine theta. So we're basically just bringing this all down, simplifying it again. And finally, we put this into a fraction right here. We go here. So it'll be F cosine theta minus the coefficient of friction, F sine theta minus coefficient of friction again, mg cosine theta minus mg sine theta, and then it's time to put it in the fraction. So we're going to put that all over m to get acceleration, because it's mass times acceleration. We're trying to find the acceleration, so we simplify this as much as we can. Then we take the m divided over here, so we just have acceleration equals F parentheses cosine theta minus the coefficient of friction sine theta close parentheses minus mg parentheses coefficient of friction cosine theta plus sine theta close parentheses all over m. And this is the diagram that we use to describe that. Final question is develop an expression for the magnitude of force F that allows the block to slide up the plane with a constant velocity. We can do that using this formula, where it's F net equals ma, which is also equal to 0, because the up and the down force, it would have to equal 0 if it's going to slide up the plane with a constant velocity. If there's no acceleration, it has to be equal to 0, which is equal to F up times down, also equal to Fx minus the force of friction. We saw that again over here, where we have x equals ff. If these are equal, the block doesn't move anywhere because they're on opposing sides. Minus mg sine theta for the weight of it. So you have 0 equals the force of x minus force of friction. Bring this over here, minus mg sine theta. We'll put it into an expression. So since this is 0, we can just add these two over here. So we'll have fx still on this side equals the force of friction plus mg sine theta. Transfer this into f cosine theta, and then we'll have the coefficient of friction times the normal force for the force of friction. And then we'll have mg sine theta, just bring that down. Bring this down again, we'll have coefficient of friction equals fy. We described this earlier, that fn equals fy, because they're going opposing sides, plus mg sine theta equals f cosine theta. Then we bring this, distribute it into the
coefficient of friction times mg cosine theta plus F sine theta equals mg sine theta. Bring this down again. Coefficient of friction, distribute this, mg cosine theta plus coefficient of friction, F sine theta plus mg sine theta equals F cosine theta. And finally, we bring this all together again. If we want to find the force, divide it by cosine. So the final equation is coefficient of friction times mg cosine theta plus the coefficient of friction, F sine theta equals plus mg sine theta all over cosine theta equals F. And we're done.